Hi, this is Kevin Iga. Welcome again to Calculus 3 video lectures. This is lecture 2. Normally lecture 1 and lecture 2 would be done on the same day. So if you're doing lecture 1, then lecture 2 would be something that you would naturally do at the same, right afterward. It's up to you, of course. And lecture 2 has to do with 13.3, the fundamental theorem of calculus for line integrals. All right, so let's begin. To begin with, let's review the fundamental theorem of calculus. The fundamental theorem of calculus for one variable functions looks like this. You've got an integral of g prime dx is equal to g of b minus g of a. So in other words, if you take the definite integral, this is the definite integral here, of a derivative, then you just evaluate the original function at these two values and subtract. Okay. One thing to notice here is that even though this ostensibly talks about an integral, talking about the values of this throughout this entire interval from a to b, actually on the right hand side this only depends on the endpoints here, g of b and g of a. Also, the way that this is used is typically you want to find an integral of something. Okay, say the integral of x squared dx from a certain number to another certain number. And this can only be done if you know that x squared is the derivative of something. In other words, if you know how to find the antiderivative of x squared. In this case, of course, you know that x squared is the derivative of 1/3 x cubed. And so you just plug in 1/3 x cubed and plug in b, plug in a, and subtract. As you know, this is how you find the integral of x squared dx from a certain number to another certain number. All right, so that's the fundamental theorem of calculus. And the fundamental theorem of calculus for line integrals looks like this. So it looks a lot like it. It's instead of a definite integral, this is a line integral. Instead of the derivative of g, we're talking about the gradient of g. So here I'm imagining g is a function of two variables, or maybe three variables if this is a function in 3 dimensions. And then I take this gradient. The gradient, remember, is a vector. And so this is a vector field, and I dot it with dr. So this is an integral of the type f dot dr, where f is a vector field. In particular, it comes from the gradient of g. And again, this is going to be g of something minus g of something. I've called this r end and r start. I'll explain what I mean by that in a moment. But the point is, this looks a lot like the fundamental theorem of calculus. All right, to explain this, what I've done here is I'm showing here a contour map of a function. Okay, so this is the level set at height 9, for example, and this is g. Okay, and this is the curve c. Okay, the curve c starts from here, goes along this path, ends there. Okay. And the point is, this is an integral of f dot dr, where f is the gradient of g. I haven't shown the gradient of g yet because that just makes it a little bit busier, but I'm going to do that in a moment. The point is, I want to show you this first. G of r end. What r end means is the place where the this curve ends, which is right there, and r start is this place right here. So g of r end is just the value of g at this point, in which case this is on the level curve here, so we know that g of this is 12 here, and here it's you get g of this point here. This point happens to be on the level curve for 9, so this would be 12 minus 9, or 3. Okay. Here is, as promised, the gradient vector field here. Okay, and so the idea is if we take this integral of f dot dr along this curve and integrate this vector field dot dr, then the answer is it's 12 minus 9 in this case, or 3. All right, here's the proof of the fundamental theorem of calculus for line integrals. Okay, it's not too hard. We start with this integral of the gradient of g dot dr. And as usual, the way we do this is we turn it into an integral over t. So you know, instead of this, I have an integral dt, and t goes from a to b here. So a to b depends on the problem, of course. It's wherever t begins and where t ends. And this is gradient of g. And the way we do it is we dot it, well, not with dr, but with dr dt multiplied by dt. The dt's cancel, and then we have the same thing as this. Okay. Now the gradient of g is just this partial derivative of g with respect to x, partial derivative of g with respect to y in this vector. If it's three-dimensional, of course, there's going to be three components with partial derivative of g with respect to z. But in two dimensions, it looks like this. Similarly, dr dt looks like this, dx dt, dy dt. If it's three-dimensional, of course, there's going to be comma dz dt. And then you take the dot product. Take the dot product, just multiply these, and add. That's what you get here. And you notice that this is precisely what is in the chain rule. And what happens when you take the derivative of g of r of t. You take the derivative of that, this is what you get. And now we use the fundamental theorem of calculus for ordinary integrals. This is the integral of a derivative. Okay, and you just plug in b into here and plug in a into here, and you get this. And this is exactly what I mean. G of wherever you are at the end minus g of wherever you are at the beginning. So there you go. That's the proof of the fundamental theorem of calculus for line integrals. Let's actually see it in action. So let's say you have this function g, x squared y. You take the gradient of g, and this one, 2xy is the partial derivative with respect to x. X squared is the partial derivative with respect to y, so that's the gradient. Suppose we take a curve given by this formula. Here's t squared comma t cubed. T is going to range from 1 to 2. You'll notice that when t equals 1, that's where we start. Plug in 1 here. 1 squared, 1 cubed, you get 1 comma 1. At the end, t is equal to 2, you're going to get 2 squared or 2 cubed. In other words, 4 comma 8. So this curve is going to start at 1 comma 1 and end at 4 comma 8. This is the start. This is the end. And what the fundamental theorem of calculus for line integrals says is if you get this integral of this vector field here, this gradient, dot dr, you just have to plug in these points into g. So g of 4 comma 8, g of 1 comma 1, which 4 comma 8, just plug in 4 and 8 into here, you get 4 squared times 8. Plug in 1 comma 1, you get 1 squared times 1. This is 128 minus 1 is 127. And this is this integral. Now, of course, you could actually work through the details, actually plugging in these for x, plugging in this for y, finding dr dt, plugging it in here, do it all straightforward. But I think you'll agree this is faster. There's no derivatives or integrals, just plug in numbers. Okay. Now, of course, this is kind of a weird case because this here happened to be the gradient of g here. So when you see an integral of this type, you might wonder, okay, is this the gradient of something? Okay, if it is, then great, you can do this. But if it's not the gradient of something, or if you don't know if it's the gradient of something, then you can't really use this method. Okay. So it's not quite as easy to use as the one-dimensional version. So here's the thing. This allows us to compute this integral of f dot dr, but it requires that f is the gradient of some function. Okay. Is every vector field the gradient of something? Not so clear at this stage. Even if you do know that it's the gradient of some function, it requires this method requires us to know that function. It's the gradient of some function. What function? We need to know that if we're going to use the fundamental theorem of calculus for line integrals. And we're going to address these issues next time. But in the meantime, let me point out an interesting feature here called independence of path. Fundamental theorem of calculus for line integrals again says this. One thing that's interesting is that on the right-hand side, we have g of the end and g of the beginning. So here's our start, here's our end. I've got here three paths. Here's C1, here's C2, here there's the funny thing, C3 here. And they all start here and they all end here. And if you have this integral of this gradient of g dot dr, it's going to give you the same answer for all three of these things. That's kind of amazing. Normally, this line integral will depend on the actual curve. But in this case, it doesn't depend on the path as long as it starts at a certain place and ends at a certain place. That's all you need to know. You don't need to know how it got there, whether it did a fairly direct route or a fairly indirect route wandering around like this. Okay, so that's going to be an important question for us to examine. So independence of path is something that we can get for an integral of f dot dr, where f is the gradient of something. Let me reiterate that the integral of f dot dr is independent of parametrization. That was always true. That's what we talked about last time. So in other words, if I go through this path, C1, somebody goes slow and somebody else goes really fast, somebody else runs and then slows down and then picks up again and then slows down and does this kind of irregular thing, all of those will have the same integral of f dot dr. And that's just because integrals of f dot dr, integrals of that type, are independent of parametrization. But if I do that on this curve versus this one, you might expect those to be different. If the f is the gradient of a function, though, then those two will be exactly the same, as well as, of course, any path, including crazy ones like this. So keep in mind the difference between independence of parameterization and independence of path. Independence of parameterization is always true. Independence of path, meaning it only depends on where it starts and where it ends, is only true where f is the gradient of a vector field. So when f is the gradient of some function that's independent of path, that means it only depends on the start and end points. Next time, we're going to address these questions. Are all vector fields the gradient of some function? Okay, I've kind of hinted at the answer here. The answer is no. So for the one variable fundamental theorem of calculus, we needed your integrand to be the derivative of something, and every function is the derivative of some other function. But not all vector fields are the gradient of something. So that's going to be a little different. Okay, so if some of them are and some of them aren't, how can we tell if f is the gradient of some function or not? And if it is the gradient of some function, what is it the gradient of? Okay. Once we know the answer to these questions, then the material that I've talked about today will become a little bit more useful to us. We can then use the fundamental theorem of calculus for line integrals. And I've indicated that this is related to the independence of path of these kinds of integrals here. One thing we've seen that is if f is a gradient of something, then this is independent of path. You might ask if the reverse is true. If this is independent of path, does that mean f is the gradient of something? And that's something we're going to discuss next time. So I will catch you next time.